Lecture 1, Introduction to the GP Model, Wave Type Excitations. So this is what I thought about talking, but after yesterday I saw that many, well, Carlo and Hélène has given already quite a good introduction to GP. So I'm gonna still keep the same schedule, but maybe I'm gonna be a little bit quicker on that. So I guess that probably I will also start touching some of the topic of the second lecture, which are more on topological excitation, so vortices in GP. Then in the second lecture tomorrow, Giorgio is going to talk about Kelvin waves, and then the third lecture that Giorgio is going to give is about quantized vortex reconnections. So if I save a little bit of time for the second lecture tomorrow, I will talk about quantum vortex knots. But we'll see how it goes. So please do interrupt me with questions. I would prefer to take all questions as soon as you have them. And I also want to say, if you want more information, well, pedagogical information about the GP model, well, there is these primer on quantum fluids written by Carlo and Nick Parker, which is really good, and is available online on the archive. So I really suggest it for you if you want a first lecture notes on that. As far as I understand, it was a set of lecture notes of your module that you gave in Newcastle several years. And then, of course, there is also this nice book by Pitaevskii and Stringari, Bose-Einstein condensation. Now there is a second edition, which includes also some chapters on superfluidity, which is also a good reference. Okay, so lecture 1, the idea was to give you an introduction on GP and wave type of excitations, and what you see here is something that you can get numerically, which is the Bogoliubov wave dispersion that you have already heard about that yesterday. Okay, so again, in a nutshell, just repeating what is a Bose-Einstein condensate. So you confine a gas, you've got energy levels, because you're dealing with the act of cooling, basically reducing the temperature mean reducing the average energy of the system. If you are in a non-interacting gas, this is exactly true. And at some point you reach at critical temperature, below which a macroscopic fraction of the boson is in the lowest energy level. And then you describe all this set of particles using a single complex field, which sometimes is called order parameter, which is psi in the Gross-Pitaevskii equation. And yes, we have already seen these two pictures, the experimental evidence of Bose-Einstein condensation in 1995, which led to the Nobel Prize. So in here you see the distribution of momentum of these BEC cloud. And in there you see the fringes of interference when you let two gases interfere. So this is really showing that you're dealing with a kind of a coherent matter state, not a normal incoherent gas. Okay, so I'm going quite quickly because we have discussed about that yesterday. About the derivation of the GP model, here I'm going to spend a little bit more time because Hélène has shown you yesterday how you can derive the GP equation in a slightly different way. So as far as I know, there are two possible types of derivation that you can do. Something along the line of what Hélène has shown you yesterday, which is you can also do in using just first quantization, and it's basically a derivation which is something very similar of the Boltzmann derivation for the kinetic theory of gases. So you treat your wave function that is normally a wave function involving all the coordinates and momenta of the particles, and you make a Gauss answer. So you make the assumption that you can rewrite that wave function as a product of single particle wave functions. And then you can derive, following these ansatz, you can derive the Gross-Pitaevskii equation. There's a nice derivation about that in a review paper by Dalfova and Strengari. But the one that I'm going to show you is a different one, and is based on second quantization and many-body Hamiltonian theory. I don't know how many of you are familiar with that, but the theory is quite simple to grasp using a classical analog. So if you're dealing with many-body quantum mechanics, you write down your Hamiltonian, which is now an operator, H, in the following way. So you've got a first part, which is essentially the operator of the kinetic energy of your fields, psi and psi dagger, of your Hamiltonian, operator field, psi and psi dagger, of creation and annihilation of particles. You can also introduce an external potential acting on this particle, and then you start putting the interaction between the operators. So in this case, you can consider the first type of interaction, which is a binary collision between two operators. That looks a little bit like that, where you've got a interaction potential between your two particles. So two particles interact, they're destroyed, they interact via this potential, and new other fields are created. And then you can go over and include also 3-particle interaction, 4-particle interaction, and so on. So the first hypothesis that is made in BEC is that the gas is dilute, so you throw away all the other type of collisions, so you just consider binary collisions. And then there are two more assumptions that you make. You make the assumption that the occupation of each level is macroscopically occupied. So you can rewrite your operator. There's a missing hat in here. You can rewrite your operator as a standard classical C field, plus, if you want, some quantum fluctuation that might still be some operators. So this is a kind of mean field assumption that you make. And the other assumption that usually is made to derive GP is to treat the interaction potential between the bosons as a delta potential. So you're just considering bosons that are interacting if they are in the same coordinate, physical coordinate. And there's the constant in front of this interaction potential is proportional to the scattering length. If you're dealing with other type of gases that might have some kind of long range, you will need somehow to change this hypothesis. And I think that there are going to be some talks in the next week that are going to be on maybe dipolar BEC. So you will see that effectively you need to change that, and as a consequence, you have a different type of nonlinear term in the GP equation. So by making these two hypotheses, you can look at the evolution of your field in the Heisenberg representation by computing this commutator, and you recover immediately the time dependent Gross-Pitaevskii equation. So this is another way of recovering it. And of course, you can see here you've got your kinetic term, you've got your external potential term, if you have any, and then you've got this term, nonlinear term, that comes from exactly the binary collisions among the bosons. And yes, we have heard yesterday already that, of course, you need to remember that your GP equation is for a complex field, psi, and it models very well quantitatively a BEC, a dilute BEC of gases, but it can be also used to model qualitatively any other type of superfluid, like helium. Of course, in helium, you don't have diluteness, you have long-range interaction, so in principle, you should take into account 3-body collision, 4-body collision, and so you might have extra terms in here, non-local terms, and so on. And that was this model was derived independently by Pitaevskii and Gross in the early 1960s. So because I work in a mathematical department, I usually recast the GP model using some parameters that I called alpha and beta in order to reabsorb all the physical constants. So this is the way that I will present all the results that I'm going to show you in the GP equation with these 2 parameters, and then using this relation, you can recover if you want to see the true physical values. You can always recover the h bar, m, and the scattering length thanks to that. So I'm going to use this equation here for the rest of the talk. Okay. And in most of the talk, I think I'm going to consider an infinite system, an infinite BEC. So there is no confining potential. So we set most of the time equal to 0 for simplicity. And we have shown yesterday that why this GP model it's a good model for a superfluid. When you can use a Madelung transformation to represent psi in terms of a square root of a real field, which is the density, and a argument proportional to the phase. So both the density and the phase are now real. You go from one equation in the complex domain into a 2 equation for these real fields. And if you define the velocity as something proportional to the gradient of the phase, and you separate real and imaginary part, you can obtain these 2 equations here, which are nothing but the continuity equation for the mass of a compressible fluid and the continuity equation for the momentum in a compressible fluid. And you see in here that you don't have any term which is proportional to viscous term. So immediately you realize that you're dealing with an inviscid fluid. This is the usual term that depends on the pressure. Once you define the pressure in your system, this has no classical analog, and this is what we call the quantum pressure. So overall, this shows you that you're dealing with a compressible, inviscid, irrotational, because the velocity is the gradient of a scalar field, and barotropic fluid. Something about the conserved quantities of this equation. If you're dealing with a one-dimensional GP equation or nonlinear Schrodinger equation in one dimension, you've got a full set of infinite conserved quantity, and the system is fully integrable. But if you are extending the dimension of the system from 2 and over, then the amount of conserved quantities just reduced to these 4. Of course, you conserve, because the system is invisible, you conserve the full energy of the system. It's given by that. Conserve the total number. If you do not assume losses or forcing in your system, particles are conserved. And of course, if you subject to your boundary conditions, in this case, if you consider infinite boundary condition, there is a translational symmetry in the problem, so you conserve the linear momentum, which is defined like that. And you can also conserve the angular momentum as usual. I want to stress something regarding the conservation of energy. So energy conservation essentially tells you that the system is time reversible. And this is an important thing. So because you don't have dissipation, so the system is essentially time reversible. But as, for example, I think Sergey is going to show you, even if the GP equation is completely time reversible, when you're dealing with wave turbulence, and you're dealing with well, when you're looking at GP in a more statistical sense, you can show that there are some irreversible process. So the system tends to go from one configuration to other configuration. So sometimes you see this type of physics exactly like when you're dealing with kinetic theory of gases, where you have no losses, but when you describe the system macroscopically in a statistical sense, you end up with a kinetic equation which is time irreversible. And I think that what Mark is going to show this afternoon is that you can split the energy into several components that have some fluid mechanical meaning using Madelung transformation. Okay, so we have also seen yesterday what is the uniform solution of the GP equation, which is the simplest solution that you can find. So if you assume that there are no spatial perturbation, so if the system is homogeneous and there is no confining potential, then essentially you can call your field psi as a field psi at infinity. This is how I call it, and you can seek for this type of solution. And what you see is that basically your solution is maintaining a constant density everywhere and is just rotating in the complex field with some angular frequency that is proportional to the mean density that you've got. And in particular, you can call this angular frequency mu the chemical potential of the system. When you include a confining potential V, then the calculation is more difficult, more challenging, because depending on the shape of V, you might be able to find or not an analytical solution for a wave function that is assumed to be just rotating in time with some angular frequency which is proportional to the chemical potential, and times a value f, which is just a solution, which is just dependent on the space. So you might want to seek for these type of solutions in your system. You can find many in principle, but the most interesting solution usually is the one that has the minimal value of the parameter mu. And so once you've found that, you can call this solution the ground state of the system. This is quite important because usually, well, when I first thought about that, I usually thought, okay, there is only one mu, so you can only find the ground state solution. There's a unique value of mu, but sometimes you can find, well, more than one solution. And later I will discuss other solutions that they do behave like that, but they're not ground state solutions. And I'm pretty sure that you all know them, but maybe you've never thought about that in this way. So this is formally the definition of the ground state from a mathematical point of view. Okay. This is probably the other only analytical solution that you can find, exact analytical solution that you can find, which is considering the problem, like in standard quantum mechanics, the problem of the semi-infinite well. So if you consider a system where, well, for instance, a unidimensional solution in space, where there is an infinite potential on the negative x-axis, and there is no potential on this side, and you look for a solution of the full system, you can find out that basically the solution has the form of a hyperbolic tangent. So this is that you can find, and the width of the hyperbolic tangent is what you can call the Hillen length, as Hélène has shown yesterday. And basically, the ground state solution in this case recovers the bulk density at infinity within usually 2 or 3 Illen. If you want, this is the one of the way of seeing the definition of the Hillen length. Another way, sorry, let me just go back. Oops. Another way of interpreting the Hillen length in the system is just to think that the Hillen length is given by the characteristic scale at which these two terms are have the same order of magnitude. So if indeed you say that this term should be equal to this other one, and you can think that this operator, which is, well, depending on the number of dimension, goes like that, is proportional to 1 over a characteristic length squared, then you find out that beta 1 over L squared times psi, that I'm going to simplify from here and here, should be equal to alpha times this value here. And if you assume that this value, the mean value, is given nothing but the mean density at infinity, then you recover immediately the definition of this characteristic length, which is the Hillen length, given by what is it, beta divided by alpha times density, which is exactly that. And there is a minus sign because this is just a, well, dimensional argument, but then you have to take into consideration that alpha and beta might have different sign. So formally, the Hillen length is just defined for a defocusing case and not a focusing case. Okay. Right, so once you found the uniform solution or the ground state solution, you can always look for perturbation on it. And we have heard a couple of talks about that. You can, for instance, if you don't have a confining potential, then the problem is analytically. You rewrite your wave function as a uniform solution plus some little perturbation. And you use these ansatz, plug it into the Gross-Pitaevskii equation, and you assume that the perturbations have some wave-like form, and you look for the dispersion relation of these waves. So you look for the relation between omega and k of this perturbation by linearizing the system. This is the same thing that Hélène has shown you yesterday, but Hélène showed you this from the fluid mechanical framework. So using the density and the phase, in here you can do the same type of calculation starting from the field psi. And so if you do a little bit of calculation, you will find out that the dispersion relation follows this function here, which is called the Bogoliubov dispersion relation. And this is an exact, perturbative calculation that you can do easily uniform condensate, but as soon as you start putting a confining potential, then it's not, most of the time it's not possible to treat to obtain analytically the ground state solution. So you're not able to do that, and you have to do it numerically, and this is what is called sometimes Bogoliubov-Desgen type of approach. So the important thing of this dispersion relation, we've seen it yesterday, at long perturbation, so at small k, the dispersion relation is linear, so you've got phonon in your system, and at short scales, you've got free particle in your system. And then you have the changes between this linear behavior to the quadratic behavior at a scale which is exactly the same scale as the Healy length, which is again an evidence of the fact that the Healy length scale is exactly the characteristic scale at which one of the two terms in the GP equation is winning over the other. And as Hélène already shown, this has been measured in BEC in 2002, doing some Bragg spectroscopy. So I'm not an experimentalist. I can't really comment that much on this, but the results of the dispersion relation are pretty convincing for a theoretician like myself. And you can, of course, measure this also numerically. So if you take the Gross-Pitaevskii equation, for instance, you take it in 2D or in 4D or in 3D, you put an initial condition which is a uniform solution with some little perturbation in it, like the one that. So this is a slice in the x domain, and this is psi mod squared, so it's the density, which you cannot really see. I think that the mean value is probably 1, and the value of the perturbation is something like 1% or 2%. If you start with this initial condition with some kind of random wave at all scales, and you let it go, you should see some, well, the dynamic is really slow in this case. There are some little changes. I don't know if you can see that. What you can do, you can, at a given amount of time, you store your psi field. So you store your psi field every, I don't know, 100 iteration, 1,000 iteration, collect many, many samples, and then from field, which now is a sample over all value of space and all value of time, you take Fourier transform time, and you take the absolute value of it, you can recover something like that. So you see, basically, for each type of wave excitation, what is the angular frequency that you measured. Okay? So you can recover numerically what is the wave dispersion of the well, you see numerically that, for instance, wave of this wave scale, wavelength, they do have a peak, a resonant peak. So they do oscillate either at this frequency or this frequency. And then if you superimpose the Bogoliubov dispersion, you can actually convince yourself, I haven't done it in here, that these two branches are the two branches that you expect from the Bogoliubov dispersion. And maybe Mark is going to show some picture of that later in his talk, not only for the field psi, but maybe for the density and so on. So it's a nice way of measuring the type of excitation in the system in a numerical. And then you can, yes? There's a physical meaning. Good question. So when you obtain the Bogoliubov dispersion relation, the dispersion relation is something that you obtain something like you've got omega squared equal to something. Okay, so of course you always have the positive branch and the negative branch. The negative branch is usually weaker than the positive branch. What is the physical meaning of it? I don't really know, I have to say. So the question is, what is the physical meaning of the negative? Well, is there a physical meaning, or is there a physical interpretation of the negative in the dispersion relation? Can you? No, it's not wave in one direction and the other. It's not that. So what is that if you're somehow looking at the system not in the right basis, so you haven't diagonalized the system in the right basis. If you look at the perturbation in the Bogoliubov basis, so if you rewrite your psi as a combination of psi and psi conjugate with the right amplitudes in it, then you will find only one the positive dispersion. So it's okay. Yeah, you're right. But physically, I mean, if what does it mean that you will see waves? It's not waves going in the opposite direction. Is what you will see, like anti excitations. Mm-hmm. Mm-hmm. Yes, along over. Yes. Mm-hmm. Yeah. Well, it's the rotation in the complex plane. So some that they do rotate together with the uniform solution, and the other one they rotate opposite to the uniform. You're right. Yeah. Yeah, because you have also both branches over there. Yeah. They don't start from zero exactly. So there's also a shift, which is given by the value of condensate. So as yes, this is true. So if you go back in here, whoa. Don't really know what I'm doing. Yeah. So if you go back in here, indeed, you're looking at the well, the Bogoliubov dispersion relation that you find is for these excitations here, but then there is also the mean value of the angular frequency at which the uniform solution is rotating. So of course, when you measure numerically, you will measure this plus mu, which is given the shift. So the shift is giving you the value of the chemical potential. So what I wanted to say is that if you do this measurement with a very tiny perturbation, you can see clearly a very well-defined line, which is very thin. So the resonance is really precise. But then if you increase the perturbation compared to the value of the density, like in this other case that I'm doing. So in here, again, the value of the density is set about 1, and I think that the perturbation are 10%. So now you clearly see that the value of the two lines of the resonance becomes broader and broader. So this is a clear sign of the fact that the system becomes more and more nonlinear. And so this perturbative approach starts to fail. Well, it's still giving you some pretty good results, but if you push it more and more, then you will see some changes in that. Okay. Right. So the last thing that I would that I wanted to also talk about, which is related to what Hélène also said, you can experimentally most of the time you put this Bose-Einstein condensate in a trap, and you can play with the type of trap. Traditionally, those traps were harmonic, but nowadays you can also build some steeper values of traps. So there is one type of analytical solution that you can construct, which is the Thomas Fermi profile, which is very easy to do. So if you want to find the solution within the trap analytically in this Thomas Fermi regime, what you have to do is just to throw away the dispersive term, so the Laplacian term, and then you find out that for an harmonic trap, your Thomas Fermi profile is just a inverted parabola. But you can do that for any type of potential that you are considering. Of course, this assumption is valid when you've got a high value of mu, and starts to fail when you've got low value of the density. So in here, in reality, you will have some opening of the density profile. The fact that in this area, then the term that you have thrown away becomes more and more important. And as Hélène said, you can with the dimensionality of the BC. So even if you start from a three-dimensional BC in a trap, confined, for instance, using a harmonic trap, you can play with the frequencies of the confinement, and you can make, for instance, one of the frequency much stronger than the other, or two of the frequency much stronger than the third one. And at the point that the frequency is so strong that on that particular direction, your Bose gas has no more degree of freedom. Well, the bosons have no more degree of freedom to move. So that direction is completely frozen. And if you do so, you can do a Gaussian approximation in that direction for the wave function, which is also the solution of the harmonic potential problem, linear harmonic potential problem. Since if you confine only in the third dimension very tightly, you can rewrite, mathematically you can rewrite your field as a two-dimensional wave function times your Gaussian approximation in the third dimension. You use this ansatz, you plug it into your GP model, and what you obtain is now a GP equation for your two-dimensional gas by averaging over the third dimension. And there's one important thing to notice, that you have now changed the value of the interaction parameter. So your G, which is in front, the G, which is what I call alpha in my notation, is now different. So it's given by the normal value of, G is now different. So it has also, it incorporates also the characteristic length of the confinement in the Z direction. And as a consequence, when you're looking for the ground state of the system, the value of the chemical potential also changes. So you have a new chemical potential in 2D given by the usual one, minus this extra value which is given by the trap. So one has to remember that when dealing with the lower dimension. And there's an interesting thing in 2D, because in this case in 2D, this quantity here is non-dimensional. So you can play with that to see some scaling behavior. And maybe Hélène is going to talk about that, I think, or maybe no. You can play, of course, the same game by by confining very tightly in two directions. And so again, you can now rewrite your mathematically your wave function as an effective one-dimensional wave function times the Gaussian confinement in the Y and Z direction. You obtain a 1D effective 1D GP model by integrating in the other two dimensions. And again, you see that your G now has changed, and as a consequence, also the chemical potential. So this is what is called a cigar-shaped condensate, and the previous one is what is called donut, no donut, a disc-shaped condensate. Yes, pancake. I don't know. I wonder if can you have some instabilities? No. Good question. I see what you mean, because it changed the energy of the well. Yeah, but yeah, this is all the focusings. No, because the definition of focusing, the focusing is contained in G, not in mu. It's just the constant at which the ground state solution rotates. So it's just a shifting up and down the energy level, I think. So that means that you need to have higher and a higher value of the density in order not to have that. So mu for a uniform solution is alpha times the density field, or minus alpha times the density field. Well, mu depends on how much density you put in it. Well, you don't have it in if you use the time-dependent equation, depending on how much density you put, how many particles you put, and if you look for the ground state solution, then you will find the value of the characteristic value of mu that you find. Mm-hmm. So what you're saying is that it doesn't play. It's just a shift. Yeah. Mm-hmm. To reabsorb it, like a phase. Yeah. So I think I'm at the end of the what I plan to be the first lecture. So okay, so maybe I can. Okay, yes, I wouldn't mind maybe going. No. All right. So as I said, the idea of the second lecture was discussing topological excitations of vortices. But before doing that, I just want to show you what type of wave solution you can find analytically in GP equation. So in principle, if you're looking for traveling wave solution, those waves, they do not necessarily have to be solitons or nonlinear waves in a strictly speaking sense. Because if you start again with the GP equation with no confining potential, and you seek for the easier type of traveling wave solution, so something that looks like that, then you can find that, of course, these solution can satisfy your equation, provided that the angular frequency has these value here. So it's a usual wave where the angular frequency depends on the wave number, shifted by the value A, so the value of the mean density of the wave that you're. So effectively, you can find this type of wave. But the interesting thing to notice is that this is not really a wave, because if you look at the density field, which gives this solution here, so if you're looking at the mod squared of psi, then the exponential part goes away, and you just have a mod squared. So this is just the uniform solution again, but which is just translating with some constant velocity. So it's the same uniform solution, just moving with some momentum. And again, this is not the ground state of the system, because it is true that you can see this as mu, but you see that in here mu is not the minimal one, which you will obtain with this, but it has also been shifted by minus alpha a mod squared, and alpha for defocusing case is negative, so you will shift the chemical potential of this solution upwards. So this is not the ground state. Indeed, this is the uniform solution moving some extra energy. And this is not really a wave type solution. Yes. Yes, so you've got a nonlinear frequency shift for every mode that in GP is a constant, and I think is exactly this value here. Yes. So if you want to find really solitary wave solution in the system, you need to consider a more involved type of solution, which is really the density and the phase at the same time. And if you are in defocusing regimes, so in this case, defocusing regime means that alpha and beta in my notation have different sign. And you consider the 1D case for simplicity, you can find out that the nonlinear traveling wave solution that you can find are called gray soliton. And they look something like that in the density field. So they're deep in the density. Far away from the dip, you recover the bulk density value. And then depending on the speed of the solution, the value of the dip is bigger and bigger inversely to the speed of the traveling wave. So if you have a gray soliton solution that does not move at all, the value of the dip reaches 0, so you've got a zero density at this point, and this is usually called dark soliton. So the full family is called gray soliton. This particular one is called dark soliton, and it doesn't move. And this is the corresponding solution that you can find mathematically. I think in here, for simplicity, I set beta and alpha equal to 1 and minus 1. But you can rewrite that in terms of generic beta and alpha. So this is the case when you have a defocusing case, and this has been observed since 1999 in Bose-Einstein condensate. What I didn't say is that this solution, it is true that this solution has a dip in the density, but has also a change in the phase of a pi from one side to the other. So this is the way that that they produced this solution experimentally. So they applied some they did some phase imprinting on the quasi one-dimensional BEC to create a phase difference from one side to the other, and then they observed how these almost precise dark soliton eventually split into two gray solitons, which are propagating into opposite direction. But in 1D, you can also show that the system is stable in the focusing regime. So if now you've got both alpha and beta having the same sign, and again, in 1D, you can construct traveling wave solution in this case, which are called bright solitons. So on the contrary, compared to the dark soliton solution, a bright soliton is a wave packet of matter, which is localized. So at infinity, the density is going to 0, and the density is maximal at the center of your wave packet. And the higher is the value of the density, the slower is the wave, the wave speed. And again, in this case, you also have an extra parameter, which is mu, so the amount of matter that you put in your bright soliton solution. And this is the mathematical solution, again, given for alpha and beta equal to 1. Also, so this has been realized experimentally by two competing groups in 2002. So they created a quasi one-dimensional BEC gas with focus interaction, so attractive type of interaction between bosons, and they studied the motion of this wave packet in the x direction. And you see in here, well, it's not really constant velocity. Probably this is due to the fact also of the kind of harmonic confining potential that is confining in the x direction. And in here you see maybe a kind of bright wave train of solitons, again oscillating. So imagine that there is a x harmonic confining potential in here, so they want to oscillate like a pendulum, okay, going back and forth. And I think I can stop in here, and tomorrow I will talk about what happens to this solution if you include, well, if you expand and look at this solution in more than one dimension.